Okay. Hello, hello. Is it working? Sorry, it took some time to set it up, but here we are. So, my name is Jacopo. I'm going to talk to you about complex cameras, and now we are trying to make it less complex. So, my name is Jacopo. I'm an embedded Linux software engineer. I mostly work on integrating camera systems and multimedia devices. Here are a few of my contacts. Here, you're welcome to ping me. And why are we giving this talk? Why are we doing this work in the first place? That's because the increasing complexity we are used to in embedded systems regarding the camera acquisition process, it's coming into canonical computing space like laptops and tablets. And Linux systems have a problem with that. Are Linux systems ready? No, they're not. And so we have a problem, and we're trying to solve that. It's pretty not necessary to state either this here in this room, but digital imaging is a complex task. It's not complex that it's complicated, but it's computationally expensive. It's computationally expensive during the acquisition phase, because you go through all the deburring and interpolation and pixel transformations. It's complex when you have to do image quality tuning, like auto balancing, white balancing, out exposure, whatever. And we usually work with very big buffers, like not that big resolution in the quite common format. It's 4 megabytes of data, and we are transporting this back and forth to different devices. If we look at the architecture of a system like it is today, like it presents itself today, regarding the image capture part, well, it doesn't go away, I'm sorry. Regarding the image acquisition part, we usually have a few acquisition ports. Today is mostly CSI too, backed by a big fat ISP. The ISP interfaces itself with system memory for doing DMA transfer of images. It interfaces with other system components like DRM. It interfaces with the CPU. It has very fast interconnection because it's a system peripheral. And externally we have a sensor, of course, that provides the image data. What's an ISP? An ISP, it's an image signal processor, which is nothing but the set of digital processing blocks that performs transformation of images. It's composed by configurable blocks, so you can create pipeline of transformation that does different kind of transformations. And what it usually does, it's interfacing with memory, so DMA transfers, rescaling, resizing, cropping, all kinds of transformations. It can convert formats from one format to another, pixel encoding, make it easier to present image to application or whatever. And it can do a lot of advanced image processing features like 3A and reprocessing, tuning, etc. It's very efficient because it's a system peripheral, so it runs a very high frequency, it has a high-speed interconnection with CPUs, and the design is very platform specific. For a system on chip that maybe are targeted to the automotive markets, you would like to have a lot of DMA channels because you're maybe transferring a lot of different images from different sources. If you have an SoC which is designed from the mobile application space, you maybe would like to have different outputs with different pixel encodings to present images like still capture or viewfinder easy to the application. That's what a system looked like 10 years ago, and the thing was kind of different from what we have today, because we have maybe one acquisition port, a few acquisition ports that usually parallel, backed by maybe a scaler, maybe a pixel converter, but nothing complex, and we just have interfacing to the system memory. Of course, the sensor outside dealt with most of the complexity at the time. That was called a smart sensor. That's why, because they were doing most of the things that nowadays run on the ISP. Video for Linux has been designed, the Video for Linux API, in a time where systems look more like this. So we have a single device node abstraction in user space that controls the whole acquisition process. That fits very well if your acquisition process is basically just moving frames to and back and forth from the system memory. of IOCTLs, which are called the media controllers, that allows you to link the different processing blocks and create different pipelines. And through the V4L2 subdevs API, that allows you to control what formats and what transformation each block performs. This is very nice and powerful. You still capture images through the device node, through the Video for Linux 2 API like it used to do. And this is very nice and powerful, but it has a problem. The problem is that the system usually doesn't boot in a usable state. Before you can do anything, you have to configure the pipeline, set up links, set up the formats. And to do that, all the applications that want to interface with that need to have a very good knowledge of the underlying hardware. So this is very platform specific. Also, to perform a capturing application is not just like we used to do with a start stream on the video device node, but you have to set up precisely all the pipeline components, because otherwise you got back an ePipe, an error, and you cannot stream. So for embedded system, this is okay, because it's acceptable, because you usually bake your own rootfs, you can embed scripts there, you can do whatever you want, it's very system specific. But if you think about something like that running on a laptop, that doesn't work for real, because distributions are not ready for that. They aim to be generic, so that doesn't work very well. And until today, that was not a problem, because most cameras on laptops and tablets were USB cameras. USB cameras are mass sensor. They just connect through a USB. They are very platform agnostic, because USB is universal. And it fits very well in the Video for Linux 2 single device node abstraction. You have a single entry point for the whole image capture process, and you control everything that goes on through that single entry point. We have a library, libv4l or V4L2, which works with most of the sensor that we have today, USB sensor, and does format conversion and makes easy to write application for Video for Linux. But something's happening, and we start receiving bug reports. That's a very recent one. It was on the Linux media mailing list 1 week ago, I guess. And basically says, I have a laptop and I cannot see the webcam. I like the concept of dual boot. That's a complex camera. It's an IPU3. It's Intel ISP. And you need a driver, of course, but you also need user space to do all the configuration and tuning, so that's not going to be supported. That's what's happening is that we start to seeing Intel, so Kaby Lake and Skylake platforms, which embed a complex ISP. And producers have started making laptops and tablets using that one. Driver is okay, is in staging right now. It has been submitted to Linux Media, so good work with that, but we're still missing the user space part, because this device simply doesn't work in Linux. That's how, just to give an idea how an ISP works, that's a simplified model of what happens on the IPU3. So we have two different blocks. One is that is in charge IMGU, imaging unit, which does all sorts of complicated transformations. And you got three different outputs, one which is scaled, one which is full size, and a set of metadata, which is used for tuning a very complex 3A and tuning machinery, which is fed to another input, which controls how the next images are captured. So this is complex, and this is a complex camera. So in order to have something like that to work, you have to bake some scripts that set up all the pipeline, all the formats in its single piece of the capturing pipeline, and that's very complicated. So a discussion starts like I think was July. There was a meeting in Tokyo for the Video for Linux community that derived meeting notes, and The issue is that we have devices which are not working. Mauro gave a very nice presentation at ELC about complex cameras and why they are complex and how they work so far. And the output from that was that a project has started, which is called libcamera, which is a joint effort between the Video for Linux community and part of some industry partners. When libcamera is not just a library, it aims to be a complete full stack in user space to deal with complex camera on Linux systems. Libcamera aims to abstract away all the complexity to setting up and controlling the media controller and the video for sub-devices. And it aims to be compatible, first of all, with Linux, because we want to solve that problem for Linux system, but also with very widespread systems like Android and Chrome OS, because a lot of devices that run with IPU3 and other ISPs are Chromebooks. In 25 minutes, I won't have time to go into technical details for that, but Laurent gave a very nice talk that details the architecture of libcamera and the internals at ELC. It's available on YouTube or the ELC website. So if you want to know more details about the technical specificities, you should refer to this talk. But I would like just to give an idea of the architecture, and that's a stack of applications that capture images. And starting from the top, we might have frameworks like GStreamer. We might have application that uses libv4l like they're doing today. We will hopefully have native libcamera application, and maybe we have Android on top of that. There will be adaptation layer, and there will be libcamera. On the camera object concept. So if you ever work with media controller, you know that nowadays we have to specify which media device you want to work on, which video device node you want to operate on. libcamera aims to the pipeline ender will receive requests for formats and capture profiles from the camera and the camera manager, and we'll apply that to the underlying hardware. As we've seen, the 3A in tuning, it's kind of important on those kind of platforms. So we design an RPC system to isolate processes that run a 3A algorithm, because those kind of processes are usually provided by the vendors. So we don't want to tie in any binary, and we want to give space for open source 3A implementation to compete with the vendor ones. So we are designing an RPC interface to isolate that process in a separate address space and interface with libcamera separately. Of course, we got a set of helpers to interface with the actual devices, and that's what we have in the application. That's a very brief introduction, and I would like to concentrate, since we don't have much time, on how we are actually doing that, because libcamera is a new project, started a few months ago, but we already have something that is usable, and it's you're welcome to interact with. So we have a Git repository which is hosted at Linux TV, where all the Video for Linux development happens. And we are doing development on the mailing list. I know, or you love it or you hate it, but that's how we decided that it was best to do that, to guarantee that we keep following a development process that is as much distributed as possible. We're using Mason and Ninja, which I don't know how many people knows that. I didn't know about those two projects before starting with libcamera, but if you use AutoTools, those two things are amazing, because it makes it very easy to distribute an application and track dependencies, and also helps with testing a lot. We do enforce a coding style, which is something that most projects do, and we do that because we want to have the code that which level of quality does it as close as possible as the kernel one. So it's partly to satisfy our OCD and have the code that looks nice, But it's also because we are using that, we are developing in C++. And C++, it's a language that makes very easy to mess up. So since a few years, there is a lot of attention on the concept of ownership since Rust came out. And doing that in C++ requires a lot of enforcing in coding style and coding rules. And in order to do that, since we are doing C++ and we don't have support from the language itself, we love peak reviews. So if you're used to the level of reviews of peakness, of reviews on the Linux kernel mailing list, that's what we aim to have. So you're welcome to bike shed on the variable declaration order, names of the variable and stuff like that. But also, we invite you to take part in that and help to keep the code quality very high, as we would like to have. We also try to be serious at documentation and testing. We found out that writing proper documentation, it's more difficult and takes more time than writing code, possibly. And we're using Doxygen for that, which is great. We generate the website from the source code as well as documentation. And we enforce testing because we would like to have all major components that gets in to be associated with the test. And we aim to have much more platform as possible that support those kind of testing. Where are we right now? The project is very young, very, very young, just 2 months old, and we have support for UVC cameras, which are the traditional USB cameras, and we have a almost fully working support for Intel IPU3, which is the first and most urgent targets that we have. We can list and detect hot plug and hot unplug of cameras, and we can capture frames actually, which is kind of a nice thing considering that until a few months ago, those devices were not working at all in Linux. Where do we want to go? libcamera ideally should support OISP that has a media controller compliant kernel support. So there are a lot of ISP that are possible targets for next development. There is Rockchip ISP. There are other platforms which has a good support in kernel space, and we aim to support all of that. Of course, in mobile space, there is a big competitor for all Linux system, which is sort of Linux system, which is Android. And Android has a very complex camera stack. If you are used to work with Android cameras, you know that camera output V3 supports per frame request. So each frame is associated with a set of capture parameters, which is something that requires development both in the library and both in the Video for Linux API, which today is not totally ready for doing that. Also, we would like to get in touch and work as much as possible with vendors, because we would like to have something like when you supply a driver for Video for Linux and for media controller, that should be associated with the support for libcamera in order to have a complete user space and kernel space support for the camera itself. One of the reasons we chose C++ for that is because we want to interface with vendors, and we know that most people there know C, maybe they're kernel developers, so it's easier for them to drag people in using a language which is more familiar. So I would also like to, well, these are a few references. We have a website, we have a mailing list where we share patches. We will have a patchwork, possibly. And we have an IRC channel, like most projects do. And you're welcome to give inputs, because the project is very young, and we want to know as much as possible for people that is working with cameras. Before going to questions, which I hope you have some, I would also like to give a brief, and I would say that's not a demo because it's very, very simple, but this device is a device as an IPU3, it's a Chromebook, as an IPU3 device, and was not supported by Linux system until a few months ago. And right now, I think we have a small utility, which is called CAM, that allows you to, right? Wonderful. So it was working before. Oh, I'm not rude. My bad. Here you go, we have 2 cameras. Wait, that's not all. And we can also capture from cameras. As you can see, you identify cameras by name. The name is now created by parsing not the ACPI table, but just parsing the sensor name. You can identify camera by calling that by name. You don't care about which media devices they are connected to. And we can capture frames, hopefully. And thanks to with a bit of conversion, there is an image there. Hey. Trust me, it's very dark because we don't have all the machinery to do the tuning in place, but at least we can capture frames, which is something that until a few times ago was not possible. So I think it's a good achievement. So I hope you have questions for me. I hope you have questions for us in general. There are other people which is involved in the project here, so feel free.
Is there any overlap between what libcamera does and what GStreamer does?
So should I repeat the question?
Yes.
Is there any overlap between what GStreamer does and libcamera does? Not really, because GStreamer is one layer up to libcamera. Nowadays, GStreamer has what is called the V4L2 SRC element, which interfaces with the video device. We hope that we will have a libcamera element where you can just interface thus asking lib
you could see in future also being picked up by the embedded community, or are they just happy with what they're doing?
So are we focusing just on laptops and tablets, or is that something that should be used also in embedded systems, or embedded systems are fine the way they are? I don't think so that embedded systems are fine the way they are, because today everyone is making his own solution. So or you have a script using MediaCTL, but it's very difficult to keep track of the resolution along the pipeline, or people maybe write their own application using the interfacing with the device drivers interface. But I don't think so that the systems are fine the way they are. So we hope to have all the ISPs and platforms that have a kernel support, which is mainline, to use libcamera as well. So I think that they are on the same level. You know, this is more pressing because you buy a laptop and the camera is not working on Linux, so that's very bad. On the embedded system, they are already used to work with that. So, yes.
So before you mentioned that the AAA algorithms are really important and that those are fed by the statistics blocks. One of the issues, as far as I know, we've had with statistics blocks is that the vendors are not willing to document their statistics info. So you have an ioctl which gives you a bunch of bytes and that's your statistics info for the capture frame. What's the situation with the IPU3? Is Intel documenting their statistics info?
Well, I should repeat the question. It's a very long one, by the way. So the problem with 3A and statistics, it's usually that it's very system specific, and vendors are not keen on giving away documentation on those things. But 3A and tuning is very important. Time's up, so I'll be very quick.
Finish your answer.
Okay, thank you. So what is the situation with IPU3? Is Intel behaving well in this case? And is Intel providing documentation? I would not say that it's providing documentation. They're doing, in a way that they are doing development on mainline. So we have the driving staging, and it comes with documentation on the parameter and everything. As far as I know, there are no private IOCTLs, which are vendor specific, so that's a good thing. So yeah, Intel is doing good on that in this case, and we want more vendors to do that because libcamera works only on mainline and standard video for Linux interface. Okay, thank you.